Another important situation where the WKB method could be applied with privilege is in the explanation of a purely quantum mechanical phenomenon referred to as the quantum tunneling, or simply speaking, say tunneling, which is a phenomenon that is being exploited for giving an explanation to alpha decay that involve the process of emission of helium nuclei by radioactive nuclei when they are subjected to natural or induced or artificial radioactive decay. And the significance of this phenomenon is that in alpha decay, the helium nuclei are, say, being emitted from the nucleus, which is a bound system having a tremendously large attractive potential. These alpha particles occupying such a very large potential or a region of strong potential will never have sufficient energy to get penetrated out of the surface of the nucleus or boundary of the nucleus. Though these alpha particles occupying within the nuclei have energy less than the energy required to overcome the barrier or the potential barrier provided by the boundary of the nucleus, they are found to be emitted. This is a situation where particles having energy less than the potential energy are found to be coming out of the potential barrier under the assumption that they have crossed the barrier. Classically, no such a system can be found on the other side of the barrier if the energy of this penetrating particle is less than the energy provided by the potential barrier. However, quantum mechanically this happens. You can have some wonderful explanation for this phenomenon if the population of alpha particles within the nuclei is so high, they are in a state of constant random motion on the course of which they will be undergoing successive collision with each other at a very high frequency, such that at some point of time they might have acquired sufficient amount of energy to penetrate through the barrier. Anyway, this involves a situation where particle having energy less than the potential energy of the barrier will be coming out of the barrier. Of course, you can have a physical intuition about the situation. Perhaps the particles might have penetrated through the barrier, so that there is no question of, say, jumping or hopping over the potential barrier. We will now consider a mathematical explanation for this kind of a situation on the basis of, say, the knowledge that we have acquired through the discussion about the WKB approximation. For that, consider a potential barrier having a definite height. This height is being represented by means of the height of this potential barrier. Let this potential is, say, having a definite peak height somewhere here. I will be completing this figure shortly. And let this be the width of this potential barrier. Say W corresponds the width of the potential barrier. And let's assume that we have a lot of particles occupying this region, and these particles are assumed to have a total energy which is a constant that is being marked as, say, somewhere here, and this is the potential or nature of the potential barrier. The height of this potential barrier is largely exceeding the total energy possessed by the particle. Classically, these particles will be occupying this region only. There is no question of any particle coming to this region by penetrating or not penetrating, by jumping or hopping over this barrier, since the total energy is less than the potential energy or height of the potential barrier. Yeah, this I will have to extrapolate like this. Now, in the language of WKB approximation, there are two classical turning points, say x1 and x2. But unlike a bound system, here the potential to which the system is subjected exceed that of the total energy in this region. So this is purely a non-classical region, whereas region 1, see this one, region 1 and region 3 are purely classical regions. If you have already a particle here, it can be found here, of course. However, once you have particle only here in the region 1, there is no question of classical particle that is being found in this region 3. However, quantum mechanical particles always have this capability of penetrating through the barrier. Of course, the extent of penetration will be depending upon the height as well as the width of the potential barrier. If this barrier is having an infinitesimally small thickness, as in the case of a tunnel diode, definitely these particles will be able to penetrate through the potential barrier, corresponding to even an infinitesimally small accelerating potential being supplied. Now we will look into the problem in the sense that particles penetrate through the barrier so that a population of particles could be found at this region 3 as well. So the particles that are found in the region 3 are at the expenditure of the loss of particles in region 1. So there must be a connection between the number of particles crossing or propagating through unit area normal to the area in this region as well as in this region. This count, that is the number of particles passing normally through unit area, is referred to as the particle flux. If it's only the total number of particles crossing unit area, not perpendicular to it, this is what you call fluence. However, here we will be making use of the concept, say, flux, number of particles crossing normally through unit area. Suppose the particles are moving from left to right in this region 1, then at this interface or at this classical turning point, a population of particles might be reflected back to the same region, whereas a small population of particles manages to penetrate through this potential barrier. As they reach at the second classical turning point, another population will be returning back, and if the particles do have sufficient energy, there is a chance that particle will be penetrating into the second classical region being labeled as a region 3. So in region 1 there could be particle moving along both left to right direction as well as from right to left direction. The particle flux from left to right corresponds to incident flux, whereas that from right to left corresponds to reflected flux. Whereas in region 3 there can be only particle moving from left to right, and this is nothing other than the transmitted barrier, transmitted flux of particles that have managed a successful penetration through the barrier. We will make an analysis at the end of which we will make some qualitative arguments that will be involving those factors which decides the transmission probability for tunneling. So basically our aim is to evaluate the transition probability, which is the ratio of particle flux transmitted to that of incident. We will represent the particle flux by the symbol, say, J, so that J with subscript TR represent transmitted flux of particles, whereas J with subscript in represent incident flux of particles. So our primary aim is to evaluate the transmission probability for tunneling, or the so-called tunneling coefficient, or the so-called transmission probability. And if you are interested, you can evaluate the reflection coefficient. This is also referred to as transmission coefficient. If you are interested, you can evaluate the transmission probability for reflection or reflection coefficient, which is the ratio of the flux of reflected particles to that of incident particles, Jr by Ji. As long as WKB or the applicability of WKB is concerned, we will be interested in evaluating the transmission probability. For that, in region 1, as I have already told you, it's a classical region. The solution, the WKB solution will be oscillatory, and there can be particles moving from left to right as well as from right to left for a positive wave propagation as well as a negative wave propagation. Plane progressive wave propagating along both the directions. So this is represented using pure WKB wave function. A1 by root p e raised to I by h cross integral x1 to x p dx prime. I hope you recall that while writing the WKB wave function, we will be taking the reference point as the turning point. Plus b1 by root p e raised to minus I by h cross integral x1 to x p dx prime. This represents a plane progressive wave propagating along the positive x direction, and this represents a plane progressive wave propagating along the negative x direction. So clearly this corresponds to the incident flux, whereas this corresponds to the reflected flux of particles. I told that correspond to, not equal to. It's a representative. The flux will be evaluated using the wave function, that I'll tell you very shortly. Whereas in region 3, there is only wave propagating along the positive x direction. So we have only one choice for this representation, which is represented as a3 by root p e raised to I by h cross integral x2 to x pd x prime. Now, as I have already told you, transmission probability for tunneling is the ratio of the flux of transmitted particles to that of the incident particles. And flux of particles by definition is the number of particles passing normally through unit area. Number of particles could be evaluated using the particle density, number of particles per unit volume, into length covered per unit time, which is nothing other than the velocity. So particle density into velocity give rise to the particle flux. And this can be evaluated from the velocity parameter or the momentum parameter. We assume that, this can be taken as, say, rho, the particle density, into momentum, or square root of momentum, whole square, provided you take the assumption that there is no question of any change for the mass of the particle if it is reflected or if it is transmitted. That is true as well. So that we can take this in terms of, say, momentum, or I can state here that it is the velocity, which is nothing other than the momentum, since there is no question of any change for the mass of the particle due to reflection or refraction or transmission. Similarly, this velocity of incident particle, and rather than velocity, the momentum magnitude of incident particle, transmitted particles and reflected particles are assumed to be exactly equal in magnitude, because this process is strictly on the basis of the conservation law of linear momentum, which is a very fundamental law as long as any branch of physics is concerned. In every kind of process, this total linear momentum will be a conserved quantity. And again, we assume that this is an elastic process. There is no question of any transference of energy, as well as these quantum mechanical particles are very truly satisfying these conditions and are able to obey these considerations as well. So the velocity parameters are exactly equal. You can omit these parameters, or you can cancel these parameters from the numerator and denominator. So what remains is the ratio of the incident particle density to that, ratio of the transmitted particle density to incident particle.
Thus, the expression for transmission probability becomes particle density of transmitted beam divided by particle density of incident beam, and this particle density is nothing other than the probability for finding these particles. So that are nothing but the square of the relevant part of the wave function. As long as the transmitted intensity of particle is concerned, it is the norm square of the wave function representing the transmitted beam, and that of the incident particle corresponds to the square of the amplitude of that part of the wave function in region 1, that is represented by, say, phi 1 incident, phi 1 with this part, say phi 1 incident. So which this ratio transmission probability is equal to phi 3 square divided by phi 1 incident square, and that is equal to A3 by root P e raised to I by h cross integral x2 to x pd x prime into complex conjugate of this one, which is now A3 star A3 square e raised to minus I by h cross into this one into e raised to I by h cross into this one. So the exponent term vanishes, divided by root P into root P, make it say P. So on the numerator you will have A3 square by P, and the denominator you will have square of this one, which is A1 square divided by P. As the momenta of the incident beam and transmitted beam are exactly equal, the momentum term also will be vanishing and the transmission probability becomes equal to A3 divided by A1 whole square. So in order to evaluate this, we are required to represent A3 in terms of A1 or A1 in terms of A3. Suppose you get A1 equal to something into A3, then you will be able to find out A3 divided by A1 equal to, say, this one. For squaring it, that will give you the square of this constant part that is to be evaluated. For that, we follow the procedure that we have formulated on the basis of the connection formulae. Let's consider phi 3, the wave function in region 3 representing the transmitted beam of particles, that is A3 by root P into this exponent, that is A3 by root P into, let me multiply and divide this by means of e raised to minus I pi by 4, that is, this is multiplied by e raised to minus I pi by 4 and e raised to plus I pi by 4, that is being added with the power of the exponent part. Now let me take this A3 into e raised to minus I pi by 4 as a constant, say A, divided by root P into e raised to I is taken out as a common factor for these two terms into 1 by h cross integral x2 to x pd x prime plus pi by 4. See x2 to x pd x prime plus pi by 4. Now this can have a de Moivre's expansion. We know that e raised to I theta equal to cos theta plus I sin theta. So that is being used here. A by root P is retained. Cos of, instead of theta, I have this quantity, and in due course I will represent it using some symbols since it is a pretty long term. Plus I sin theta, sin of this quantity is repeated 1 by h cross integral x2 to x pd x prime plus pi by 4. Now we apply the connection formulae to the wave function in region 3 so that the wave function in region 2 can be obtained. A by root P is the constant that is being taken out here. Now this is a sinusoidal oscillation representing the classical region 3. This cosine wave function needed to be shifted into an increasing exponential term e raised to 1 by h cross integral x to x2. X is an arbitrary point here and x2 is the point here. This is how we will be applying say connection formula, plus I is there, and this sine wave function needed to be replaced by means of a decreasing exponential term with the constant multiplying the decreasing exponential getting halved. So I is the constant as long as sine wave function is concerned. This is to be halved for the decreasing exponential. So I by 2, decreasing exponential is e raised to minus 1 by h cross integral x to x2 pd x prime. Now we make a substitution. Here also we have integral from x to x2. That can be clubbed with a constant integral from x1 to x2 as integral from x1 to x2 pdx prime, the overall integral, which will be a constant. I will be representing this constant using this parameter, say capital theta. That's equal to integral from x1 to x pdx prime plus integral from this arbitrary choice of x to x2 pdx prime. So that I have an intention of making a substitution for integral from x to x2 pdx prime. That will be equal to integral from x1 to x2 pdx prime minus integral from x1 to x pdx prime. So that from this point, say x and x2, I will have a shift to x1 and x. And in the very immediate step, I will be again applying connection formula so that I will get a wave function representing the region, say 1. So we will make this substitution for integral from x to x2 pdx prime in terms of integral from x1 to x2 pdx prime and integral from x1 to x pdx prime. Then phi 2 becomes a by root p e raised to 1 by h cross integral x1 to x2 pdx prime minus is there, that is being taken as a second exponent term e raised to minus 1 by h cross integral x1 to x pdx prime. Now onwards I'll label this as say capital theta as I have told you, plus the second term is I by 2 is here e raised to minus 1 by h cross integral x1 to x2 pdx prime. If this is positive, it is being labeled as a theta. So if it is negative, if the power is negative, definitely this will be 1 by theta e raised to 1 by h cross integral x1 to x pdx prime. There are two different minus signs that will make this term say positive in power. Now a by root p, this is labeled as theta e raised to minus 1 by h cross integral x1 to x pdx prime plus I, this is 1 by theta, so I by 2 theta e raised to 1 by h cross integral x1 to x pdx prime. Now again we apply connection. So we have now reached the first turning point, say x1. We require the wave function in the region 1. For that again we will have to apply connection formula for the wave function written in region 2. Then we will be applying again connection formula. We obtain then the wave function in region say 1, that is phi 1, which is equal to a by root p. Theta is the constant and this is a decreasing exponent. This is to be replaced by a sinusoidal oscillation with constant multiplying the sine oscillation being twice that of the decreasing exponential. So I have a multiplication by 2 here. Sine of 1 by h cross integral from x to x1 pdx prime plus pi by 4. I'll label it say m from the next step onwards plus I by 2 theta. This increasing exponent needed to be replaced by means of a cosine wave function with no modification for the constant. Constant I by 2 theta is repeated. Increasing exponent is replaced by cos of 1 by h cross integral x to x1 pd x prime. I have forgotten a pi by 4 plus pi divided by 4. That is, now we substitute a as a3 into e raised to minus I pi by 4. Here e raised to minus I pi by 4 is multiplied here, and here a3 is written here. 2 theta is already there. This is now sine m. Sine m can be written as say sin theta using De Moivre's theorem. As you know, sin theta equal to e raised to I theta minus e raised to minus I theta whole divided by 2i, and cos theta equal to e raised to I theta plus e raised to minus I theta by 2. Those substitutions are being made here. So this is sine of m. M is this entire quantity. So again in this step I have repeated this term itself, e raised to 1 by h cross. So instead of 1 by h cross I will have I by h cross integral x to x1 p dx prime plus pi by 4 minus e raised to minus I theta. Instead of this I have put here m divided by 2i into this a3. A parameter will give me a3 and e raised to minus I pi by 4. And for this term I by 2 theta is retained. Cos theta is e raised to I theta plus e raised to minus I theta by 2. I have a lot of theta parameters here, so that is why I have labeled it m. That labeling is not necessary, it's only for the sake of convenience. Divided by 2 into e raised to minus I pi by 4. Now there are two terms, one containing e raised to im, another one containing e raised to minus im. So we take them together, and before that we will be opening this bracket using e raised to minus I pi by 4 as well. For this term e raised to minus I pi by 4 and e raised to plus I pi by 4 will be vanishing, whereas for this negative term e raised to I by h cross x to x1 p d x prime minus pi by 4 plus pi by 4 plus minus I pi by 4 make it minus I into pi by 4 plus pi by 4, that is minus I into pi by 2. Minus e raised to minus I pi by 2 is cos pi by 2 minus I sin pi by 2, that is minus I. So in this term there is a scope for minus I. This term in the exponent term with negative power there is a scope for minus I here as well as here, whereas in this term this pi by 4 parameter will be going. So let me take this term first. E raised to I by h cross integral x to x1 p d x prime plus pi by 4 minus pi by 4 make pi by 4 getting vanished. What remains is I by h cross integral x to x1 p d x prime, that is being labeled as a q now onwards. For this step I have taken this as it is, and the coefficient is 2 vanishes. I in the denominator is minus I in the numerator, so minus I theta into e raised to I by h cross integral x to x1 p dx prime minus this second term is e raised to minus I by h cross integral x to x1 p dx prime into this expansion that I have told you, which will make it say e raised to minus I pi by 2, which is minus I, that is written here, plus I by 2 theta into 2 I by 4 theta e raised to iq. See, this term is labeled as a q plus e raised to minus iq into minus I. Now let's take e raised to iq, the positive power terms together and the negative power terms together. The positive power term here, once it is taken out, the constant part becomes minus I theta, plus in this term e raised to iq is taken out, what remains is I by 4 theta into e raised to I by h cross integral x to x1 is here p dx prime plus, and the second term get modified as you have minus I and minus sign here, minus minus make it plus I. Upon opening this bracket you have I coming from the bracket and minus I theta here, making it minus I square theta. Minus I square is plus 1, so the coefficient for this term will be theta, and for this term this coefficient will be minus I into plus I by 4 theta, that is minus I square, which is plus 1 by 4 theta. So theta plus 1 by 4 theta into e raised to minus exponent term. that is a3 by root p into theta plus 1 by 4 theta e raised to I by h cross integral x1 to x p dx prime. See, this term is... So, to make a comparison with the WKB wave function, we will take this term negative because in WKB we will be writing integral from x1 to x for region 1. So, how to negate this power term as well as this power term. So, this will be getting modified as positive. That term is taken first, theta plus 1 by 4 theta. This power limits of integration are altered so that this minus term becomes plus e raised to I by h cross integral x1 to x p dx prime. And from this term, let me take minus I outside. Minus I into what remains is theta minus 1 by 4 theta into e raised to minus I by h cross integral x1 to x p dx prime. This limit of integration is also negated. Now we make a comparison of this wave function that we have formulated on the basis of connection formulae with the WKB wave function in region 1. So, the coefficient of e raised to I by h cross integral x1 to x p dx prime is a1 by root p. We can omit root p, so this is a1. And that of this negative power term is b1. We have obtained phi 1 using connection formulae, say this one. So the coefficient of this positive exponent term happens to be theta into theta plus 1 by 4 theta into a3. So this should be identical with a1, so that we can take this as say equal to a1, and this parameter must be equal to b1. a3 into this parameter must be equal to b1. a3 is outside the common curly bracket. That is being taken here. a1 equal to theta plus 1 by 4 theta into a3, and b1 equal to minus I into theta minus 1 by 4 theta into a3. This minus I coefficient is an indication of the phase change upon reflection, or is an indicative of reflection, as this an exactly similar derivation you might have met in first semester while you talked about the reflection of electromagnetic radiation at a lossy medium, or at the interface of two media, while you talked the electrodynamics. So the transmission probability or transmission coefficient T, as we have already obtained, is a3 by a1 whole square. So I'll have to put a1 to the right side, and this coefficient is taken to the left side. What remains is a3 by a1 on the right side, and I'll have to square it. Then that will be equal to 1 by theta plus 1 by 4 theta whole square. That is theta plus 1 by 4 theta whole raised to minus 2. Since this quantity is in the denominator, the parameter, the contribution of this quantity is much smaller comparing with this parameter. So approximately this can be taken to be say 1 by theta square, or theta power minus 2. And I hope you recall theta, that's equal to integral from x1 to x2. Of course e power is there, exponential power integral from x1 to x2 p dx prime. So square of this one with a minus power is, this power term will have say minus 2. That is, transmission probability for tunneling is e raised to minus 2 by h cross integral x1 to x2 p dx prime. See, this is a decreasing exponential parameter. So the transmission probability will be falling exponentially, very rapidly, with two different quantities that include or that decide the momentum parameter. The momentum, as you know, is given by root of 2m into e minus v. 2m into e minus v. As the momentum parameter increases, the transmission probability decreases. There are two choices for the momentum parameter to increase. First one, that is, say, e minus v is the parameter. When v is much larger, that is height of the potential barrier is very large, then e minus v will be very large, that is momentum will be very large. Under such a situation, transmission probability will be infinitesimally smaller. Another parameter that decides the transmission probability is integral over dx. The dx is the thickness from x1 to x2. If this quantity increases, x1 to x2 range increases, then also this integral increases. That also account for a rapidly falling transmission probability. So we conclude transmission probability falls exponentially with first one, height of the potential barrier, number 2, width of the potential barrier from x1 to x2. So these are the two parameters that control the transmission probability for tunneling. And I have already told you, if you are interested, you can evaluate the reflection coefficient, which is b1 by a1 whole square. b1 by a1 can be obtained by dividing this equation by this equation. b1 by a1 will be there on the left side, and on the right side a3 vanishes. What remains is minus I into theta minus 1 by 4 theta by theta plus 1 by 4 theta whole square. That is theta minus 1 by 4 theta whole square by theta plus 1 by 4 theta whole square. We are not going to simplify it. Of course, it's of the form a minus b whole square by a plus b whole square. And if you sum up this is also a wonderful result that also may be asked for probing as long as your examination is concerned. The sum of transmission and reflection coefficients will be equal to 1. This is something that you have also discussed in electrodynamics as well. The sum of transmission and reflection coefficients will be sum of, say, this one with this one. So they have a common denominator, that is theta plus 1 by 4 theta whole square. So their numerators are to be added. 1 plus theta minus 1 by 4 theta whole square whole divided by common denominator theta plus 1 by 4 theta whole square. Now this is of the form a minus b whole square plus 1. Here a minus b whole square is theta square plus 1 by 4 theta whole square. A square plus b square terms are theta square plus 1 by 4 theta whole square. A square plus b square. Now you have minus 2ab. That is minus 2 into a is theta and b is 1 by 4 theta. Theta vanishes. You have 2 and 4 making it, say, 2 in the denominator. Now this is a square plus b square minus 2 plus 1 is here. A square plus b square minus half plus 1 is here. That is a square plus b square plus 1 minus half, that is, say, plus half. But we have seen that 2ab is equal to plus half. 2ab is equal to half. So that now this is of the form a square plus b square plus 2ab. That is nothing other than a plus b whole square. That is theta plus 1 by 4 theta whole square. So the numerator and denominator vanishes. You will get this, say, equal to 1. With that, we come to an end for the discussion on WKB approximation. In the examination point of view, this module, or say this portion of the module, is very important. You can have 3 Surely you can have 3 questions from this module, or say from WKB approximation, and one of these will be a short answer. Most likely short answer is criteria for the validity of WKB approximation. The second possible question is describe the principle of WKB approximation, and a third possible question in short answer section is describe the Bohr-Sommerfeld quantization principle. Most likely choice for essay is obtain the general expression for energy eigenvalue of a bound system, explain its significance. That is the derivation of Bohr-Sommerfeld quantization principle along with a supplementary problem. Either that could be the case of a linear harmonic oscillator or hydrogen atom. And generally you can have a problem that will be most often an application of the Bohr-Sommerfeld quantization principle. So make your preparations about this approximation procedure very well. In the next video we'll move on to the approximation method, the one and only approximation method that we will have to talk about as long as time dependent problems are concerned, that is time dependent perturbation theory.